to do is quickly review the log rule for integration. So remember, the integral of 1 over x dx is just equal to the natural log of the absolute value of x plus c. Or if that x is instead a function in terms of x, like it is here, 1 over u du, the integral of that is still going to be the natural log of the absolute value of u plus c. Again, this is just letting you know that the log rule for integration holds up under u substitution if in the denominator you have a function in terms of x. We're also going to quickly review the derivatives of the 6 basic trig functions. That would be sine, cosine, tangent, cosecant, secant, cotangent. You need to have each of these derivatives memorized. Same thing with the integrals of the 6 basic trig functions, sine, cosine, tangent, cosecant, secant, and cotangent. Have each of these integrals memorized. Same thing with the derivatives of the inverse trig functions. So arcsine, arccosine, arctangent, arccosecant, arcsecant, and arccotangent. You need to have each of these derivatives memorized. All of these derivatives and integrals will appear on the AP test, and you need to have them memorized. Now, the last set of things I need you to memorize involving trig functions would be the integrals involving inverse trig functions. So there are 3 that are tested on the AP test. The integral of du over the square root of a squared minus u squared is going to be equal to arcsine, or the inverse sine of u over a plus c. The integral of du over a squared plus u squared is going to be equal to 1 over a times arctan, or inverse tangent of u over a plus c. And the integral of du over u rad u squared minus a squared is equal to 1 over a times arcsecant, or the inverse secant, of the absolute value of u over a plus c. So when you see these functions we're taking the integral of, they should be pretty familiar because they were the derivatives of these inverse trig functions that we talked about earlier. The only catch here is what we're taking the arcsine of, or the arctangent of, or the arcsecant of. Also this 1 over a multiplied out front of the arctan and the arcsecant. Now this integral where you get arcsine and this integral where you get arctan have appeared on the AP test most often out of all of the integrals involving inverse trig functions. This one, the integral where you get arcsecant, has appeared on the AP test, but very rarely. So I recommend that you memorize all 3, but if you're just going to memorize 2, it would be these 2 right here. Now, we just told you that the integral of du over the square root of a squared minus u squared is equal to arcsine of u over a plus c, but where in the world did we get this formula? Well, let me show you. So we know that the derivative of arcsine of x is equal to 1 over the square root of 1 minus x squared, meaning the integral of that would be arcsine of x plus c. The only issue is what happens when this number right here is not 1, and this over here is a function in terms of x, not just x. Well, here's what we're going to do. To show you how we get this formula, what I'm going to do is I'm going to factor out an a squared from each of the terms in the radicand here. Now, the reason I do that is because if I have the square root of something times something else, I can break it into 2 separate radicals where it's the square root of a squared times the square root of 1 minus u squared over a squared. And the square root of a squared just becomes a. Now, how does that help us? Well, what I can do now is use u substitution in order to integrate this, except I already have a u in the problem, so I can't use u substitution. What I'm going to do instead is use another variable, so we'll call it y substitution. So I'm going to set y equal to u over a in here. The reason is because when I take the derivative of this with respect to u, the derivative of y with respect to u is going to be dy du. The derivative of u over a, remember u is a function in terms of x, a is just a constant. So technically I can take 1 over a, move it out front, and just take the derivative of u with respect to u, which is just going to be 1. Multiply both sides by du, I get dy is equal to 1 over a du. Now, again, how does that help us? Well, we look at the problem. We have a 1 over a, because our a is in the denominator, du. So we can substitute in dy for that du over a. Now all we have to do is rewrite this integral in terms of y and dy and integrate it. So y, we said we're going to substitute in for u over a. Dy, we're substituting in for 1 over a du. We now have this integral where it's the integral of dy over the square root of 1 minus y squared. Exactly what we said the derivative of arcsine was. So when we integrate this, this is clearly going to be arcsine of y plus c. Now what we have to do is take what we set y equal to, which is u over a, plug it back in for y, and we've derived this formula that we have for the integral of du over the square root of a squared minus u squared. Now I want to do the same thing with you, but now for the arctan formula. Because again, you're looking at this formula like, where in the world did this 1 over a and this u over a come from? Well, we know that the derivative of arctan of x is just 1 over 1 plus x squared. Meaning the integral of 1 over 1 plus x squared dx would equal arctan of x plus c. But the issue is, what happens when this is not 1? What happens when this is a function in terms of x instead of just being x? Well, here's how this works. What I'm going to do is I'm going to, again, factor out an a squared from each of these terms in the denominator. When I do, I get something that looks like this. Now again, how does this help us? Well, what we can do is rewrite this u squared over a squared as the quantity u over a squared, because that's a property of exponents. Now, after this, we're going to again use u substitution. But again, we have a u in the problem already, so we're going to use y substitution, because all we have to do is pick another variable in order to substitute. So I'm going to pick y. So I'm going to let y equal u over a. Now the reason is because when I take the derivative of this with respect to u, over here the derivative of y with respect to u is going to be dy du. Over here the derivative of u over a with respect to u, remember u is our function, a is just a constant. So technically I can take 1 over a, just move it out front and take the derivative of u, which is 1. So I get 1 over a times 1, or just 1 over a. Multiply both sides by du, I get dy is equal to 1 over a du. We look at the problem. Oh, we have du over a squared, not du over a. So what do? Well, I need this to be 1 over a squared. So I'm going to multiply both sides of this equation by 1 over a. I can do that because 1 over a is just a constant. So if I multiply it to both sides of the equation, that's fine. Now what I can do is I can rewrite this integral in terms of y and dy. I'm going to substitute y in for u over a, and I'm going to substitute 1 over a dy in for 1 over a squared du. Now remember, this 1 over a is just a constant that I can move out front of my integral sign, and now I can integrate this because we said we know what the integral of dy over 1 plus y squared is, right? It's arctan of y plus c. We multiply that 1 over a on, and now all we have to do is take whatever we set y equal to, plug it back in for y here, and we've derived this formula that we have for the integral of du over a squared plus u squared.
Ants have been around since the dinosaurs. It's example time.
Now example 1 says find the indefinite integral. So here we are taking the integral of dx over the square root of 4 minus x squared. Now we look at those three integrals involving the inverse trig functions, and this kind of looks like the one involving arcsin, except it's supposed to be a squared minus u squared down here. Well, remember, u is just a function in terms of x, so u can equal x. That's fine. What about over here? This is supposed to be a squared, and we have 4. Well, in order to get a, what we have to do is square root whatever this number is. So this number is 4, therefore the square root of 4 is 2. So we can rewrite 4 as 2 squared. Now it's in the correct form, the integral of du over the square root of a squared minus u squared. So all we have to do is take our u, which is x in this case, plug it in here. Take our a, which is 2, plug it in here, and we have evaluated this integral. Part B, doing the same thing. So again, we have an integral that looks like it's in the form of the integral of our inverse trig function involving arctan, or inverse tangent. But remember, this is supposed to be a squared plus u squared. Well, u is equal to x in this case, so that's fine. But what about a? Well, this is just 2. So remember what we did up here. We have to take the square root of this number in order to get a. So we're going to rewrite this integral as dx over the square root of 2 squared plus x squared. Now we can see that this perfectly fits that mold for the integral involving arctangent. We have our a value as rad 2, so that's going to go in here and here. We have our u is just going to equal x, so that's going to go in here, and we have successfully evaluated this integral.
What do you call an ant who likes math? An accountant. You try.
Okay, doing the same thing. We again have an integral that looks like it's the integral involving arctangent. But recall that this is supposed to be a squared plus u squared in the denominator. Our u is just going to be x, that's easy. But over here, this is supposed to be a squared, and it's just 16. Well, in order to get a, what we have to do is take the square root of whatever this number is. So that's going to be 4. So we can rewrite this integral as dx over 4 squared plus x squared. Now we can see what our a value is and what our u is. So we can take our a, which is 4, plug it in here and here. Take our u, which is x, plug it in here, and we have successfully evaluated our integral. Down here, doing the same thing. This time we have our integral, and it looks like it's the one involving arcsecant. So if you recall, in the formula that we talked about, our denominator is supposed to be u rad u squared minus a squared. So u is clearly going to be equal to x, but our a squared is equal to 25. So the question is, what is our a? So all we have to do is just take the square root of this number, and we can rewrite this as x rad x squared minus 5 squared. So looking at that formula then, we see that our u is going to be equal to x, like we said, instead, and our a is going to be equal to 5. So we take x, plug it in for u, take 5, plug it in for a here and here, and we have successfully evaluated this integral. Example 2, doing the same thing. Now we again have an integral that looks like it's the one involving arctangent. However, in our denominator, it's supposed to be a squared plus u squared. So we want to rewrite this so it at least looks like it's in the formula a squared plus u squared. So the question is, how do we find a? Well, if this is supposed to be a squared, we just take the square root of this. So the square root of 2 is going to be a. Over here, this is supposed to be u squared. So the question is, what is u equal to? What do I have to square in order to get 9x squared? Well, that would be 3x. So this is now in the form a squared plus u squared. Now there's one thing that trips up everybody in these types of problems. When this is not just x, when your u is not just x, it's some function in terms of x, you can't just go and plug this in the formula and call it a day. Because this is a function in terms of x, you need to use u substitution. You have a function within a function. So you're going to set u equal to 3x in this case. The reason is because here, I'm going to have to take the derivative of both sides with respect to x. Derivative over here of u with respect to x is du dx. Derivative over here is just going to be 3. Multiply both sides by dx, I get du is equal to 3 dx. We look at the problem. If I'm substituting u in for 3x and du in for 3 dx, well, there's only a dx. There is no 3. So what I have to do is take this constant and divide it to the other side of the equation. Now I can rewrite this integral in terms of u and du. I could take u, plug it in for 3x. I could take 1/3 du and plug it in for dx. Now I can evaluate this integral. So this 1/3 is just a constant. I can move out front of the integral sign. I can now evaluate this integral using that formula that we know for arctan, and then I multiply that 1/3 on the front. Then what I can do is take whatever I set u equal to at the beginning, 3x, plug it back in for u, and I have successfully evaluated this integral. Again, when this right here is not just x, when it's 9x squared or 16x squared, when it's a function in terms of x, you have to use u substitution, otherwise you'll get it wrong. You'll forget this little constant that should have been multiplied out front.
What do you call an ant who's a big deal? Important! You try!
Okay, doing the same thing here. We want to evaluate this indefinite integral. Now, initially, this looks like it's in the form of the integral involving arcsecant, where in the denominator you have u times the square root of u squared minus a squared, except this can't be u, right? U is a function in terms of x, and this can't be a because a is just a constant, so these are switched. So, instead, this is actually in the form of the integral involving arcsin, because that's where we have the square root of a squared minus u squared. So then what happens with this guy out here? Well, let me show you. We're going to use u substitution in order to integrate this. So because this is in the form of the square root of a squared minus u squared, you know a squared is equal to 1, meaning a is just going to be the square root of 1, which is 1 still. So I can just leave it like this. This over here is u squared, meaning ln of x in this case is going to be our u. So when we use u substitution, we're going to set u equal to the natural log of x. I then have to find du. So I take the derivative of both sides of this with respect to x. The derivative of u with respect to x is du dx. Derivative of ln of x with respect to x is going to be 1 over x. Multiply both sides by dx. I get du is equal to 1 over x dx. And look, in our problem, we have 1 over x, because our x is in the denominator, times dx. So I can then rewrite this integral totally in terms of u and du. I can substitute u in for ln of x. I can substitute du in for that 1 over x dx. Now all I have to do is integrate this. And we now know that the integral of du over the square root of 1 minus u squared is just going to be equal to arcsine of u over 1 plus c. We can then take whatever we set u equal to in the beginning of the problem, which was ln of x, plug it back in for u, and we have successfully evaluated this integral up here. Now we got a special case that I want to show you. So we want to evaluate each of these indefinite integrals. Now notice the only difference between each of these indefinite integrals is that in this one, the x is in the denominator, in this one, the x is in the numerator. And just that one difference will cause the way you evaluate them to be drastically different. So up here, we see that this integral is in the form of the integral involving arcsecant, where you have in your denominator u times the square root of u squared minus a squared. Now the only question is, what is u equal to and what is a equal to? Well, if this is u rad u squared minus a squared, then u would clearly have to be equal to x. Well, what about a? Well, if this is supposed to be a squared, then a would have to be equal to the square root of 1, which is still just 1. So now, in this form, we can clearly see that u is going to be equal to x and a is going to be equal to 1. So we plug each of those into their corresponding spot in this formula over here. We simplify and we have evaluated this integral. Note that in this particular integral, u was equal to x, and it wasn't a function in terms of x. This wasn't 9x squared or 16x squared. That's why we didn't have to use u substitution. But if this were 16x squared or 9x squared, we would have had to use u substitution. Down here, again, the only difference between these two integrals is that this x is in the denominator, this x is in the numerator. But we're going to evaluate them two different ways, because up here, this was in the form of the integral involving arcsecant. This is in none of the forms that we have seen involving any of the trig functions. So what we're going to do instead is we're going to rewrite this integral and integrate it just using u substitution like normal. We're going to rewrite the square root of x squared minus 1 as x squared minus 1 to the 1/2 power. We then bring that to the numerator and give it a negative exponent. Now what we can do is use u substitution in order to evaluate the integral, because we have a function within a function times another function. So I'm going to set u equal to whichever function, if I were to take the derivative of it, would include the other function. So I'm going to set u equal to x squared minus 1. The reason is because if I take the derivative of this with respect to x, derivative of u with respect to x is du dx, derivative of x squared is going to be 2x to the first, derivative of negative 1 is just going to be 0. Multiply both sides by dx, I get du is equal to 2x dx. And look at our problem. We got an x and we got a dx. Perfect. The only problem is we don't have a 2. So what we do is we take that constant, divide it to the other side, and instead of substituting du in for 2x dx, since there's only an x and a dx, I'm going to substitute 1/2 du in for the x dx. So that's what I'm going to do. I'm going to rewrite this integral in terms of u and du. I take u, substitute it in for the x squared minus 1. I take 1/2 du, substitute it in for the x dx. We then can evaluate this integral. First thing we have to do is prepare it for integration. So I'm going to take this 1/2, move it out front of the integral sign. I now can integrate using the general power rule, where I get u to the negative 1/2 plus 1 over negative 1/2 plus 1 plus c. I then simplify and I end up getting u to the 1/2 plus c. Now all I have to do is take whatever I set u equal to at the beginning of the problem, which was x squared minus 1, plug it back in for u, and then rewrite this 1/2 exponent as the square root, and I'm done. I have evaluated this integral here. Note that the only difference, again, was that here the x was in the numerator, here the x was in the denominator. When it's in the denominator, we can't use u substitution like normal. Instead, we have to use one of those integrals involving inverse trig functions. Now we got a challenge problem. So we are again evaluating this indefinite integral. So how do we do this? Now this integral is strange because it's technically a combination of the two special cases that we just talked about. Remember, if we had just x in our numerator over this radical down here, we could change this radical into a 1/2 exponent, bring it to the numerator, and then we could evaluate using u substitution. If it were just 2 in our numerator, we could bring the 2 out front of our integral sign, and then we could evaluate using one of the integrals involving inverse trig functions. So what do we do here? Well, since this function in our numerator has 2 terms, and our denominator is only 1 term, this big square root right here, we can technically put that square root under each term in the numerator and give them their own separate fractions. So we can rewrite it as x over rad 4 minus x squared plus 2 over rad 4 minus x squared. And then, by our properties of integration, we can integrate each of those separately. Now, just like I said, each of these integrals now represent one of the special cases that we just talked about over here. Since our x is in the numerator, what we can do is we can take our denominator down here. Instead of being the square root of 4 minus x squared, we can rewrite that square root as a 1/2 exponent, bring that denominator up to the numerator, and make it a negative 1/2 exponent. Over here, we can take this 2, move it out front of the integral sign, and now this is in the form of the integral involving arcsin, where our denominator is going to be the square root of a squared minus x squared. And since 4 is going to be a squared, to find a, we just square root it, we get 2. So we rewrite 4 as 2 squared. Now we can integrate each of these separately. Over here, this is going to be easy. We just use our formula for arcsin. Here, we need to use u substitution, just like we talked about. Because we have a function within a function times another function, we got to set u equal to whichever function, if I were to take the derivative of it, would include the other function. So I'm going to set u equal to 4 minus x squared. The reason is because if I take the derivative of this with respect to x, the derivative of u with respect to x is du dx, derivative of 4 is going to be 0, derivative of negative x squared is going to be negative 2x to the first power. Multiply both sides by dx, I get du is equal to negative 2x dx. We look up here. We only have an x and a dx, and I can only substitute it in for exactly what's there. So I'm going to take this negative 2, this constant that's not up here, move it to the other side of this equation, and now I can completely rewrite this integral in terms of u and du. I can substitute u in for the 4 minus x squared. I can substitute negative 1/2 du in for the x and the dx. Now I just prepare both sides for integration. Here, this negative 1/2 is going to come out front, and I can integrate u to the negative 1/2 power using the general power rule. Over here, we said this was the integral involving following arcsin. So we just have to plug in 2 for a in that formula. We have to plug in x for u in that formula. Then we simplify, and we end up getting negative rad u plus 2 arcsin of x over 2 plus c. Now to finish this off, we have to take whatever we set u equal to in the beginning of the problem, plug it back in for u, and we have successfully integrated this indefinite integral up here.